Welcome to This Explainer. If you've ever felt completely overwhelmed by algorithms, you're in exactly the right place. Today, we're going to break down a foundational programming algorithm step by step. So let's just dive right in. Imagine trying to find a secret message buried in a massive wall of random text. And it's not just about finding the right letters, it's about finding them without losing your place, making sure they show up in the exact right sequence. That's the exact problem we're solving today. It sounds kind of complicated, right? But we're going to use a surprisingly simple technique to crack it. Okay, here's our roadmap. We'll kick things off with a string matching challenge. Master two-pointer logic, break down the code step by step, trace exactly how it succeeds and fails, and finally, wrap up with some tricky edge cases. All right, part one, the string matching challenge. So here's our mission brief from a coding exercise called Rewrite. We basically need to build a program that takes two separate strings. The goal? We have to verify if the first string can be constructed using characters from the second string. But here's the catch, and it's a big one. We absolutely must respect the exact order of the characters as they appear in that second string. If we pull it off, we print the string. If we fail, or if we just get the wrong number of inputs, we output absolutely nothing. Which brings us to part two, mastering two-pointer logic. To solve this elegantly, we can't just brute force it. We need the right tool for the job. And instead of just blindly looping and starting over every single time we find a letter, we use two-pointer logic. This simply means we're using two separate variables acting as our pointers to keep our place in both strings at the exact same time. It's literally a game changer for efficiency. To really visualize this, think of it like a scavenger hunt. Pointer J is our scout. The scout runs ahead, scanning every single letter in our big block of text. The scout never stops moving forward. Pointer I, on the other hand, is our tracker. The tracker is basically holding our checklist, which is string 1, and only moves down that list when the scout radios back to excitedly say, "Hey, I found an exact match for your current letter." Let's move right along to part 3, step-by-step code breakdown. Now that we've got the core concept of the scout and the tracker down, let's actually look at some code. We're using Go syntax here, but honestly, this logic applies to basically any language. First things first, we check our arguments. We need exactly 2 strings provided by the user. If we don't get exactly 3 arguments total, because let's face it, users never do what you expect, the program just returns nothing and terminates immediately to prevent a crash. If we pass that check, we just assign our target pattern to a variable called S1 and our search checks to S2. Next up, we initialize our variables. Both our tracker I and our scout J start right at position 0 at the very beginning of their strings, totally ready to start the hunt. Now for the real engine of our program. We wrap this inside a loop that runs until one of the strings runs out of characters. Inside, the logic is incredibly simple. Step 1, check for a match between the tracker's current letter and the scout's current letter. Step 2, if they match, increment I to move the tracker forward. Remember, it only moves on a match. And step 3, whether they matched or not, always increment J to keep the scout moving forward. And when that loop finally finishes, we check our results. If our tracker I perfectly equals the total length of our target string S1, what does that mean? Well, it means every single character on our checklist was found in perfect order. That's our green light to print out the completed string, followed by a new line. Okay, part 4, tracing success and failure. Reading code is great and all, but tracing it proves it actually works. Let's trace a real success story. Say we're searching for the word "faya" hidden inside a huge jumble of letters. Notice how our scout J scans rapidly through index 0, 1, 2, 3, but our tracker I only increments when that first F is found, and then it just waits patiently until the first A is perfectly matched at index 8. The scout does a ton of walking, while the tracker just holds its ground. As we keep tracing, the scout just keeps on moving. We eventually grab the Y at index 14, and that final A way down at index 21. Because we found all 4 letters in order, our tracker I reaches the value of 4, which is the exact length of the word "faya." Total success. But, we also have to look at what happens when it fails. Here, we're searching for the word "error." Our scout starts scanning and successfully finds the first E. Awesome. But then, the scout keeps running and eventually just hits the very end of the second string without the tracker ever finding all the remaining RROR characters. Because the scout ran out of search area before the checklist was complete, our I tracker never reaches the target length. The program silently fails, outputting nothing, exactly like it's supposed to. Finally, part 5, edge cases and wrap up.
You know you've mastered an algorithm when you can handle the edge cases. But first, what's super interesting here is comparing our rewrite program to another classic coding exercise called Hidden P. They use the exact same two-pointer logic under the hood, that identical scout and tracker method. They just output different results. While rewrite prints the actual string, Hidden P just prints a simple 1 for success or a 0 for failure. It just goes to show that once you master a core algorithm, you can use it to solve all sorts of different problems.
And this table really highlights those extreme edge cases perfectly. What if the first string is just totally empty? Well, our tracker starts at 0, which is already the length of an empty string, so it instantly succeeds and just prints a new line. Or what if the second string is impossibly short? The scout hits a brick wall immediately, the tracker never finishes, and it correctly prints nothing. The logic holds up brilliantly, no matter what weird inputs we throw at it. And there you have it. By assigning one variable to scan ahead and another to strictly track our progress, we solved a pretty tricky matching problem with just a few lines of really elegant code. Now that you've got this beginner-friendly step-by-step tutorial down for the scout and tracker method, think about this. This exact two-pointer logic is used everywhere in computer science. From sorting arrays to managing computer memory, it's absolutely fundamental. So my question to you is, where else could two pointers optimize your code today? Thanks for hanging out with me on this explainer, and happy coding.